Okay, we're going to continue looking at matrices and their properties and how to see more things that pop up when we work with these matrices. In particular, we have talked about operations on matrices, and we've covered addition, subtraction, multiplication, both scalar multiplication and matrix multiplication. We've seen things like the fact that matrix multiplication is not commutative. We've talked about identity matrices. We have seen that properties like the distributive property and the associative property hold. But there's one thing that's missing that we've actually mentioned before, which is division. And we didn't define division, which, if you think about it, makes sense. I mean, if I had something like some matrix 1, 2, 3, 4, and I wanted to divide it by some other matrix 1, 7, 2, 6, how exactly would that work? I mean, would you go component wise, or like, that just doesn't seem to make sense. So we need to kind of come at division from a different way of doing things. And one of the ways we have looked at this is in terms of thinking about our matrices algebraically, meaning we created algebraic expressions, something like ax equals b, where all of these were matrices. And we said, well, I can essentially solve, or I would like to solve that algebraic equation using algebra applied to a matrix. And we have actually kind of sort of done it already for some of them. If there was a constant out in front here, I could just divide that constant, because I can divide constants, and then that works fine. If I maybe had matrices added together on the left, I could just subtract one of them over to the other side. We did all this. Again, the one operation, if I get distracted while I talk, there's like a whole flock of geese walking right outside my window, so I just can see them. So we have done all these operations except for division. And, well, it's because the idea of division seems a little odd. But if we think about it algebraically, if I had something like, again, thinking algebraically, ax equals b, if I wanted to solve for x, how would I do that? The normal way of doing it that we think about it algebraically is I divide by the coefficient of x. So I divide by a, and I get x equals b over a. Again, if I had something like 3x equals 9, I divide 3 over on both sides, and I get x equals 3. The problem is there is another algebraic way of looking at this, a more general way of looking at it that kind of encapsulates all of this. And it's what's called the idea of an inverse. Meaning, if I have ax equals b, I don't actually divide by a to solve that. What I do is I multiply by the inverse of a on the left. Algebraically, what this means is a inverse times a gives me the identity, which is 1. And now I just get x equals a inverse b. That looks a little bit weird, but it's actually just the same thing as what we did here. If a is 3, I multiply by the inverse of 3. We all know what inverses mean. That means reciprocal, essentially, when we think multiplicatively. So the inverse of 3 would be 1/3. But then I multiply by 1/3 on both sides. 1/3 times 3 is 1, which gives me x. 1/3 times 9 is 3. So it's the same thing, but rather than writing it with numbers, which is what we're used to, or even throwing letters in here, now I want to use this algebraic way of writing it, which is in terms of an inverse. And an inverse actually has a formal definition. Here we will just say A inverse is the inverse of A. And again, all of you have done algebra and found inverse functions before. It's the same notation. Raised to the negative 1 means inverse. More than likely, when you learned about inverse, and I know this because I teach pre-calc and I mention it, the tendency from a student perspective is to think, well, the negative 1 power means you flip it, reciprocal, which isn't true. But again, thinking algebraically, that's kind of how it works. When you do say F inverse composed with F, that is not a reciprocal, it means the inverse. But to a certain extent, if you took the reciprocal, that's F over F, which cancels out, and gets you back to where you started, which is what the inverse does. So they're not the same, but they're kind of, sort of, the idea makes sense. That's why we use the notation. Same idea here. A inverse is the inverse of A if A inverse times A. Now, since we're talking about matrices, I multiply the two matrices together, I get the identity matrix. Ones along the diagonal, zeros everywhere else. And that's also equal to A times A inverse. We have to define it this way because, again, multiplication is not commutative, so A inverse times A is not necessarily the same as A times A inverse. In this case, it happens to be true because of the way the inverse works. But since we know in general BA is not the same as AB, we have to make sure we know if we're talking about multiplying on the left or multiplying on the right. Which means when we do all these operations out and kind of work with matrices algebraically, we have to decide, are we multiplying here or here, and do it accordingly. Again, if I had AX equals B, I could say, assuming these are invertible, we'll kind of see what makes them invertible later on. But for right now, if they are invertible, I can multiply by A inverse on the left. That is not the same as multiplying by A inverse on the right here. Here I multiplied the A inverse on the left. Here I multiplied it on the right. That does not work. If I'm going to multiply on the left, I have to multiply on the left because of this idea of non-commutativity of matrix multiplication. Now, A inverse times A would give me the identity, which is 1, and I would just get X equals A inverse B, which again is not the same as BA inverse. Order of multiplication matters here. So there's little details like that we'll have to worry about. And we're going to expand on this a lot. But again, the basic idea is, now, if I have an equation, matrix equation, I can do my operations, addition, subtraction, multiplication by a scalar, matrix multiplication. Those all work. The one thing I couldn't do before to solve the equation is division. But now I understand that division is really this idea of multiplying by an inverse. So now I can algebraically solve these equations out using all my regular operations. And then I can solve the equations just like I did in pre-calc all before. It's linear algebra. It's just applying the same algebra as before. I just replaced division with multiplication by an inverse because that's the actual more algebraic way of thinking about it. So then we are kind of stuck with the question of, do all matrices have inverses? And unfortunately the answer is no. We can actually see right away. Suppose that A is an M by N matrix, where M is unequal to N. So suppose I have a matrix that is rectangular. It's not a square matrix. Columns and rows are not the same. Well then, let's see. If I did A, which was an M by N matrix, well then, if I multiplied it by A inverse, I would need to get the identity. Well, what identity would I get? clearly, if this is an m on the outside and an n on the inside, the only way to multiply these would to let this be an n, and then the outside, because the identity would have to be a square, would have to be an m. And I would get the m by m identity. But then, what if I did the multiplication on the other side? A inverse times A, where again, A is m by n. The only way I can multiply these is if now this term is an m, and because the identity is a square, this has to be an n. And now I get the n by n identity. And m is unequal to n. Which means, depending on which side I multiply my inverse, I get a different identity. But the definition says A inverse A is equal to the identity, which is equal to A inverse. Which now clearly isn't true if I'm getting two different identities. All that means is, if my matrix is not a square matrix, if m is unequal to n, then it's not invertible. So we can restrict ourselves when we talk about inverses to square matrices. The problem is not all square matrices are invertible. We're not going to go into the algebra today on what makes them invertible. For right now, I'll just hope that all the ones I pull out of the air are invertible, and then we'll see how to find the inverse, and then later on we'll explore what's actually making it invertible, and can I determine ahead of time if it's invertible or not? You can. So, suppose I have some matrix. We're going to restrict ourselves to 2 by 2 matrices. You can do it with 3 by 3s. The algebra is the same. There's just more of it. So we're going to restrict ourselves to 2 by 2s here. And suppose I have some matrix A. We'll go with 1, 2, 3, 4. That'll work right there. Suppose I want to find the inverse of that. Well, let's see. That means I need some A inverse. It's got to be a square matrix, so it's going to be a 2 by 2. So A11, A12, A21, A22. I need to find that, and I know A dot A inverse has to equal the identity, which means A, 1, 2, 3, 4, times A inverse, A11, A12, A21, A22, has to give me the 2 by 2 identity, 1, 0, 0, 1. Now just use my multiplication and set up a big system of equations. So right over here, let's see. First row, first column. A11 plus 2A21 has to equal first row, first column, 1. First row, second column, A12 plus 2A22. I'm sorry, first row, second column, yes. A12 plus 2A22 has to equal first row, second column, 0. Second row, first column, 3A11 plus 4A21, 3A11 plus 4A21 has to equal 0. And second row, second column, 3A12 plus 4A22 is equal to 1. Now I have my system and I just have to solve it. And clearly looking at these two equations involve A11 and A21. These two equations involve A12 and A22. So I can solve them separately. For these right here, I'm going to use the one that's set to 0. So I get 3A11 equals negative 4A21. Divide the 3 over. Again, these are not matrices anymore, they're all just numbers, so I can do all my regular operations. A11 equals negative 4/3 A21. Plug that in up here. I get negative 4/3 A21 plus 2A21 equals 1. Multiply everything by 3. I get negative 4A21 plus 6A21 equals 3. 6A21 minus 4A21 is 2. So 2A21 equals 3. A21 equals 3 over 2. Now that I have A21, stick it in right here. A11 equals negative 4/3 times A21, which is 3/2. The 3's cancel, negative 4 over 2 is negative 2. Now do the same with the other two. I'm running out of room on my board, so I'll scribble it right over here. Let's see. I will solve the second one since it's set to 0. And I get A12 is negative 2A22. Plug it into the bottom one. I get 3 times negative 2A22 plus 4A22 equals 1. Negative 6 plus 4 is negative 2A22 is equal to 1. So A22 is negative 1/2. And then stick that in up here. A12 is equal to negative 2 times negative 1/2, which is positive 1. And now, let's see. There's A11, there's A21, there's A12, there's A22. So, if I just plug in here, A11 is negative 2. A first row, second column, 1, 2 is 1. A21 is 3/2. A22 is negative 1/2. Now check it to see if I actually did all this correct. Just multiply it out. So really quickly, if I multiply these out, 1 times negative 2 is negative 2. 2 times 3/2 is 3. 3 minus 2 is 1. So that works. First row, second column. 1 times 1 is 1. 2 times negative 1/2 is negative 1. 1 minus 1 is 0. 2 for 2. 3 times negative 2 is negative 3/2. There. 4 times 3/2 is 6. I'm sorry. 3 times negative 2 is negative 6. 4 times 3/2 is 6. Negative 6 plus 6 is 0. 3 times 1 is 3. 4 times negative 1/2 is negative 2. 3 minus 2 is 1. So I get the identity. Which means, yes, I had to do a little bit of algebra, but I found the inverse. I could actually check it by flipping these and doing A inverse times A. I'm not going to take the time to do that, but you can check it and it will certainly work. But now, we can erase all this algebra. From a mathematical perspective, once you define an inverse, okay, an inverse is a thing where if I multiply it by the matrix, I end up getting the identity matrix. Okay, that works. Then mathematically you say, how many inverses are there? Or put another way, is the inverse of a matrix unique? Again, hearkening back to the algebra that you remember from pre-calc, if you have a function and you find the inverse of the function, is the inverse function unique? Same idea here. We have a matrix, we can find an inverse. Is the inverse unique? Well, let's check. Suppose that little S with a curl means suppose that. Suppose that A is an invertible matrix, which just means that it has an inverse. So suppose that B is the inverse of A. I want to show that B is unique, or that I can find a second matrix, a second inverse. So now what I'm going to do is, let C be an inverse of A. So either B is an inverse and C is an inverse and they're different, or I need to show that C is the same as B and has to be the same as B. The proof is actually pretty straightforward. Well, let's see. AB is equal to the identity I, because A times its inverse is the identity. Now, multiply by C on the left. I get CAB is equal to CI. On the left here, we know that matrix multiplication is associative, which means I can move the parentheses around, and this is the same as CA, B. On the right, C times I is the identity, 1, which means C times I is C. Again, I actually do just want to stress, understand what this is saying, the associativity here. I can multiply A and B first, and then multiply by C on the left. That's the same as multiplying C times A first, then multiplying B on the right. I just want to make sure we're clear on what the associativity means and what's going on here. Because as a student, I got confused by it. But now, C times A. If C is the inverse of A, then C times A gives me the identity. So that's IB equals C. But now the identity is 1. 1 times B is just B. And I get B equals C. Which means if C is an inverse of A and B is an inverse of A, then C equals B. Therefore, see if I can write correctly. The inverse of a matrix is unique. Every matrix that is invertible, meaning it has an inverse, has only one inverse. Which I would point out, again, if you think about them in terms of inverse functions, makes sense. You only get one inverse. But now we can do a simple little algebraic proof to prove that that is actually true. There's a few other properties that we can get. In one of the other videos, we were talking about the cancellation law. AC equals BC does not imply that A equals B. Meaning, from an algebraic perspective, I can't just cancel the C, because it's common on both sides, and get A equals B. The cancellation law doesn't hold. But now, suppose that C is invertible. With inverse, we'll just say C inverse here. Now look at the cancellation law again. AC equals BC. Now multiply by the inverse on the right. AC C inverse is equal to BC C inverse. C times C inverse is the identity. So I get AI. C times C inverse is the identity equals BI. Multiplication by the identity doesn't change anything. And I get A equals B. By the same token, if I have CA equals CB, now multiply by the inverse on the left. C inverse CA equals C inverse CB. Again, this gives me the identity times A, identity times B, which gives me A equals B. So in both instances, cancellation holds. The cancellation law holds. We'll even say that. Which again means, if you have an invertible matrix, it makes solving out matrix equations a whole lot easier, because you can do this trick multiplying by the inverse, which is like division, and your cancellation laws actually hold as well. So just keep in mind, as we are working with these matrices and solving matrix problems out, you cannot assume the cancellation law holds. You cannot assume that the matrix is invertible. For right now, we'll kind of sort of assume it, or you'll be told that this matrix is invertible, because we haven't actually, like I said earlier, determined what makes them invertible. We'll see that later. But if nothing else for now, we know that this idea of invertibility only occurs if my matrix is a square matrix, and I have a way to find it. Just take the square matrix that I have, multiply it by an arbitrary matrix set equal to the identity, create a system of equations, and solve it. Again, the equations to solve, you end up with a bunch of them. We had 4 because we had 4 variables to solve. If you did it with a 3 by 3, you would have 9. But you can see, just looking at the ones we had, it's actually not all that hard to solve those equations out because of the way the inverse works. You will get practice with that on homework. All of you have taken some form of calculus, so you kind of understand how this works. You learn the limit definition of a derivative. You practice with that definition a whole bunch, and then you start learning tricks like power rule, product rule, quotient rule. Same idea here. I want you to be able to algebraically find the inverse of a matrix, and then later on we'll find a shortcut formula that will allow us to just pull the matrix out of the air, kind of like the power rule or the product rule. And when solving problems, if you know that your matrix is invertible, whether you can prove it, which we'll see later, or you're just told it, then you can apply things like multiplying by the inverse and the cancellation law to solve out matrix equations. We are going to continue with this. Again, as I've said before, there's a whole lot here, notationally and kind of definitionally speaking. It's all the algebra you already know applied to this new thing called matrices, so we have to go over every single thing again. So we will continue with this. I do have to say though, again, like I've said before, this is the first time I've taught this class, and it's the first time I've actually really seen linear algebra since I took it as an undergrad a long time ago. It all comes back to you pretty quick, and it is so fun. I enjoy it so much more now as an instructor than I did as a student, because it's not new. It is the algebra you already know, just looked at slightly differently, but it's based on all the algebra you know, because in actuality, all the algebra you know is kind of based off of this, linear algebra. So just kind of, again, as I've said before, keep that in mind as you work with this. We're following the same ideas from the algebra you know, just expanding on it slightly because of this idea of a matrix. If you would like me to do more examples of finding inverses of matrices, feel free to let me know. Like I said, I did one on the video. If you want me to make a video going through more examples of that, feel free to let me know. But I'm going to assume that the algebra solving those systems out isn't that big of a deal. So you should be fine. But if not, it's not a big deal. Just let me know.